Hello, everybody. Welcome back to the course on modern theory of semigroup. So we will resume with the next part, which is to expose known example of abstract and concrete semigroups, which, as one introducer already said, was not obviously trivial because in comparison to K-theory, these things are usually really hard to compute. Just before we begin, a quick comment about last time in the proof of the continuity of the functor. In the proof of injectivity, the claim of that I used in the subjectivity is also needed to ensure that the sequence we construct that will attain our element is actually increasing. So either reverse the order of the proof of injectivity and subjectivity, or just use the claim in the second part, in the first part also. Okay, so example of semigroup. So I will present mainly two types of examples. So one that are coming from certain sister algebras, and other that comes from abstract setting. Okay, so let us start with something that we have already seen somehow in the previous talks. So what is called, I mentioned semigroups. So these things will mainly can be realized as concrete semigroup coming from AF algebras. Okay, so for the class of AF algebra, at least in the separable case, we understand very well what's going on. So we have seen that for a finite dimensional sister algebra, the semigroup of one building block is this thing, which is the natural number with one infinity point. Okay, and I recall that the order is the usual order, the sum is the usual sum, this thing being absorbing for the sum, and the greatest elements, and all the elements will be compact apart from the infinity point. Okay, so we have this thing, if and only if, and it's actually bounded by m in the order, and this guy is not compact. Okay. So now if you take several building blocks, you will just get several copies of this thing, and it can be convenient to normalize. Okay, so sometimes it's convenient to divide any of this guy by the size of the unit of the algebra. Okay, so now about inductive limits of these things. Okay, so I will just compute some example that we have already seen, which is mainly the UHF algebras. So this will be like a toy case, and similar argument can be replicated. Okay, so we start with A being UHF algebra, and I will even take like an infinite prime, and I will take the to infinity, but similar thing can be done for any infinite prime and actually any UHF algebra. So I recall that this is algebra is built as an inductive limit where the building block are matrices of size 2 to the power of n, and the morphism are given by just putting two copies of whatever matrix you get at the end stage. Okay. And okay, so I think Francesco already dealt with this object, and Ramon also, and they computed the uncompleted version of the semigroup. And if you recall, you had all these these uh, these numbers divided by some power of two. Okay, and okay, to compute the actual complete version of the semigroup of this, we can use the construction that I exposed last time. So recall that we can actually compute the pre-semigroup of this thing and then complete it by the completion factor. So we get that VCUOA. So we have to compute this thing, and then we will just complete it. I mean, we will complete it in some way to get the consumer group of A. So this is the limit in pre-CU. So recall that in this case, pre-CU, like the pre-consumer group of this thing is just the consumer group equipped with this auxiliary relation, which is the compact containment. Okay, so we will have to compute this first, this algebraic limit, where the objects are just at each stage, it's this guy. Okay, then we normalize it, and the morphism is not hard to see that you just multiply the rank by 2. Okay, and the auxiliary relation is just this compact containment relation. Okay, so I already described what it was. And okay, so now if we normalize this thing to make things easier, we get actually this inductive system. Okay, and I recall that the limit is built as the algebraic limit, okay, with an algebraic sum, meaning that we sum we sum two elements at the final stage, and we compare two elements for this auxiliary relation at the final stage also. Sorry, and now it's the identity or the inclusion, however you feel like to see it, and it's with this normalization, now it's really checked that VCU of A is this set, and okay, and we get this auxiliary relation, which is based on this guy, and okay, so where I recall that this set is all these numbers. Wait. And now to compute the semigroup of this star algebra, which we have to complete it in the way I presented last time, which gives us that Cu of A is this gamma completion. Okay, and I recall that this means that we consider increasing sequences for this auxiliary relation, and we take equivalence classes uh, of sequences like that. Okay, and now you can compute that you will get a copy of this thing, and there will be a positive real line that will appear. Okay, so I will explain how this is done in a rough idea. And you also get, okay. So why is that? So this will correspond to actually constant sequences, okay? Because they're based on the compact containment relation. If I take an element at a finite stage, it compares with itself, and I can just like take at each stage the same elements. Okay, so this will be really the equivalence class of constant function. Okay, the infinite points. So the infinite point, I cannot consider I cannot consider a function that attains the infinite at some finite stage because it doesn't compare with itself. Okay, so the way to realize this element as a equivalence class of such a sequence is to take just the intrinsic sequence of natural numbers. So I take one at the first stage, then two, then three, and so on. So it's this guy is and this is okay. So this is it's not hard to check that it's an increasing sequence for this relation, and the equivalence class is will be the highest element. Okay. And those guys are obtained by, so if you fix a positive real number, okay, so general knowledge tells you that these things are dense in the positive real numbers. And so you just take such a sequence and the equivalence class will give you a real number. Okay, so those guys are obtained by density of these sets. So what's going on is that more or less the auxiliary relation we have is just the order. Okay, so in this case, it's really computable, and it's really nice to see what was going on in concrete. I didn't precise, so there we have some mixed sets, so we have to precise how the sum and the order are working. So, okay, mixed order and addition. Okay, so obviously the order and the addition will work component-wise on each of the separate sets. And the mixed ones are defined that way. So if I take, so I don't want to enter too much in detail, but this will correspond exactly to compact elements. So we've seen the definition of what's a compact element. And those guys are what will be called soft, but just think of them as non-compact elements. Okay, so For any compact element, I have a non-compact copy of it. So if I sum a compact and a non-compact element, I will just realize the sum in the non-compact guys and get the non-compact elements. Okay, so this actually. Okay, so I just consider the non-compact version of this guy and make the sum in this subset. Okay, so in other words, the positive real line is an absorbing subset of this thing. For the order or the way below, we have that the non-compact copy of any guys in here will be below its compact version, and those guys are compact. So this is why I don't put order, but something stronger. And this will be compactly contained in the non-compact copy where I added any small amount. Okay, this is how it goes. So I already mentioned this. But let me write it. So any guys in here is compact, and obviously this absorb any other element. And this guy is not compact. Okay, so we have an explicit description of this semigroup. Okay, if you take any other infinite prime, you will get the same computation, changing the 2 by p. And if you get any other UHF algebra, you just get a different description of the compact, and now it's just some integer divided by some finite product of the prime that appear in your construction of the UHF algebra. But this can be done pretty much similarly, and you will always get this copy of the extended positive real line that will appear as non-compact guys. Okay, so a remark on these things. So this, you can notice, we've seen this before. This is isomorphic to the Kuntz classes of projections. So to its Murray von Neumann semigroup. Okay. So we're obviously in the stably finite case. So we have this nice identification in full generality. And another way to realize the semigroup of A, so it can be checked that this thing is actually also the completion of this pre-CU semigroup. Okay, so this is another monoid, and this is an auxiliary relation for this other monoid, and you can say that it satisfies all the axiom of being a pre-CU semigroup. And if you take the completion process, namely consider star increasing sequences in this thing, which are actually just this part, then you will get the same result. Okay. So overall, CU of A can be realized as the completion of its compact elements together with the order. Okay, and such semigroup are kind of special because they have a lot of projection. A lot of compact elements, and at the level of system algebra, it means you have a lot of projection available in your system algebra. and it's a property called real rank 0. And this kind of thing will be called algebraic CU semigroup. Just think of it as CU semigroups that has a lot of compact elements, and so much that actually they are dense in your semigroup. Okay, and one may wonder if this characterizes CU semigroup of AF algebra. The answer is no, because other sister algebra have this property of having a lot of projection. Okay, so real rank 0. But it is true that the semigroup of any, probably I should put separable, but maybe not, of AF algebras are of these types. Okay, so we have this theorem. So this is actually the theorem is actually characterizing the semigroup of any separable unital AF algebra, but I don't want to enter too much detail. So by Ramon, Francesca, and Hannes in 1418, depends on if you look at the preprint or the publication. So we have that for any AF algebra, then okay, so the first part of the statement is has been already proved by, I guess, Francesca in earlier talks. So in the stably finite case, the compact element corresponds exactly to the Cuntz class of a projection, and in this case, the Cuntz class are the Murray-von Neumann class of projection. So we always have this identification in the stably finite case for stably finite. But I will be using this in some other parts, so it was good to recall it. And we always have that when I consider this order monoid with the order is kind of a trivial auxiliary relation that makes this thing a pre-CU semigroup. And I take the completion, and I always get something. I mean, I always get the semigroup of A. Okay. So this gives you a really nice tool to compute the semigroup of AF algebras. So it's kind of looking at the Murray-von Neumann semigroup equipped with the order. This will give you the compact element, and you almost get everything, and you just have to consider classes of increasing sequences of compact elements. Okay, so in particular, any elements in the semigroup of an AF algebra can be written as the supremum of a sequence of compact elements. Okay, and this is really, really useful. Okay, so this is like a first type of semigroup. A second type that has appeared also quite early in the literature is and we've seen this a bit before several times, is spaces of lower semi-continuous functions. So this is kind of finite and approximately finite dimensional case, and this will correspond more or less to the commutative case. Okay, so those are two, I don't want to say basic classes of system algebra, but two well-known classes of system algebra, and we have an explicit description of their semigroup most of the time. The spaces of our semi-continuous function so in the following, X is a compact Hausdorff space, and most of the time I will take second contable so that it's become metrizable. Okay, but for now I don't need this assumption. So what does it mean? Okay, and S here. So if I take any CU semigroup, so it can be abstract also. We consider and we write LSC of X comma S to be the set of function from X to S such that F is lower semi-continuous. And what does it mean to be lower semi-continuous? It means that the pre-image of this set for any element is open in X. So it's really a continuity condition for, I will explain more. So I already used this notation, but the arrow were pointing down and up is the same meaning. So this set is just all the elements in the CU semigroup that compactly contain S. Okay. So it appears that this type of set, okay. Okay. So it appears that this type of set are a basis for open set of a certain topology in S, which is called once again the Scott topology. So this is also coming from domain theory once again. Okay. Probably the remark. So I don't want to enter too much in detail about this thing that is coming from domain theory, but the open sets are upper sets. I mean, probably it's easier to define the closed set. So you can think of this as lower sets that are closed under suprema of increasing sequence. Okay. So there are explicit definition for open sets also, but I don't want to enter too much in detail. So knowing this, we remark that these things is just the set of continuous function from X to S, and S is equipped with the Scott topology. Okay, so you have a topology defined on X because it's a compact metric space, and on any CU semigroup, there is a topology, an order theoretic topology based on this, which is called the Scott topology. And the closed set, once again, are lower sets that are closed under suprema of increasing sequence. And being lower semi-continuous from X to S is nothing more than being continuous for the topology of A level. Okay. So this type of spaces have been studied a lot, and I will present some results without doing the proof because don't have time to go over everything, but the following theorem helps us to construct more examples based on these things. I forgot. Yeah. So here, observe that this set has an obvious pointwise sum and order. And a priori, we don't know whether this thing is a CU semigroup again or not, okay? So we have to work these things out, and it's not going to be true always. But in some nice cases, it is, and this is what the following theorem is stating. So this is done by Ramon, Francesc, and Luis Santiago in 2011, and probably some preliminary work in some special cases by Robert in 2008. Okay, so we have X compact Hausdorff space, and now we take an abstract semigroup that is countably based. So probably we've encountered this notion before, but it means that you have a countable dense subset. Okay, so it's kind of the analog of being separable. Actually, any separable sister algebra will give rise to a countably based CU semigroup. Okay, so it's a countability condition, and we have the following results. So if X is a finite dimensional space, then it is true that this thing equipped with the pointwise addition and order this is a CU semigroup. So it's really nice. So if you start with a CU semigroup and you take any compact Hausdorff space that is finite dimensional, you can produce another good semigroup that is way bigger, obviously. But okay, so this is a useful tool. And how to, so this is abstract semigroup and how to link this to commutative sister algebra. So in the case where X is second countable, so in other words, is metrizable in this compact Hausdorff space setting, and the dimension of X is less or equals than 1, then for any sister algebra A that has special properties that Ramon already mentioned. So we want no obstruction at level of K1 and probably stable rank 1 or a stably finiteness hypothesis. So any sister algebra A of stable rank 1 and no K1 obstruction. So this, I recall, means that the K1 of any ideal is trivial, and the K1 of the algebra also. We can compute that the Cuntz semigroup of the commutative sister algebra C of X tensor with A is actually one of those spaces. So okay, probably A needs to, no, maybe a separability condition on A. Probably is true in full generality, but just to link this with one, if A is separable, this thing will be a countably based CU semigroup. So this thing is a CU semigroup, and the CU semigroup you obtain is actually the concrete Cuntz semigroup of this sister algebra. Okay, and this isomorphism is actually explicit. So this you can see as sister algebra of continuous function from X to A. Okay, and so now if you take a positive element there, it's going to be a function from X with value in A plus, and its Cuntz class will actually naturally give rise to an element in there. So it's the function that sends X to the Cuntz class of f of X in A. Okay. So what this theorem says more or less is that in this really special setting of stereo rank 1 and no K1 obstruction, we can lift local Cuntz comparison to global. Okay, and Raman already explained why those two assumptions were needed. But this is really what the theorem is stating. Okay, so there is. Probably a few remarks are in order. So stable rank 1 and K1 obstruction are needed to yeah, to have local to global description of the Cuntz equivalence. Okay, so I will make this precise at the second part of the talk. Okay, so this is 1 and 2. This class of sister algebra this can be seen as pretty restrictive, but it's still kind of big. For example, it contains all AF algebras and all simple AI algebras. Okay, I recall AI algebras are interval algebras. So you take the continuous function over the interval and you take direct sum and building blocks and inductive limits of these things. Okay, there is a third example of in this theorem. So back to the theorem. So this sister algebra appears a lot in the literature, and also certain pullbacks of these things are pretty useful. Okay, so if more we have a star homomorphism from a sister algebra B to a quotient of C of X tensor A, So B can be pretty general from any just algebra B and any quotient. Okay. Then we can make a pullback from this morphism to the quotient map there. Okay, and we can realize the pullback in the C star category. And this will be isomorphic to realizing the pullback in the category of CU semigroup. Okay, so there is kind of a lot I'm hiding. So what is a pullback in the category CU? So you have to realize the pullback as a monoid and then show that this pullback is a semigroup. Okay, but these proofs are quite long and technical. So yeah. But this will be useful to produce more examples. So the conservative group of this pullback. So we have C of x plus R A, where x and A are as nice as in 2. We project down into a quotient, A, given by a closed set Y, and then we have any star homomorphism from B to the quotient, so we can realize the pullback in the category C star. And the conservative group of D is actually isomorphic to realizing this pullback in CU. So I will just pass the objects and the morphisms in the category CU. So now this is the conservative group of this quotient is the lower semi-continuous function on the closed set into value CU of A. The quotient map is given by restriction. Okay. And you can realize the pullback. So the way to do it is to realize the pullback as order monoids. And then the actual object you get is a semigroup. And this is isomorphic to CU of D. Okay. So there are a lot that I'm not saying, and this is really far from being trivial. But this could be an entire talk. And unfortunately, we don't have time to go over the proof of this. Okay. So, I mean, this is kind of technical, but the main point is that I want to apply this to some nice example. Okay, so to give you some more explicit example, probably an observation. So in all of the above, if S is the extended natural number, okay, meaning that A will be a finite dimensional C star algebra or just a complex number, then we get that okay. The conservative group of COX, and more generally, we've seen that tensoring with matrices is not changing the conservative group because it's a stable object. Is isomorphic to this thing, okay, and X, okay. Dimension of X has to be smaller than 1, and X has to satisfy the nice property that I told, okay. So all of these heavy results, in particular, helps us to compute the conservative group of commutative C star algebra of where the topological space is of dimension smaller than 1. So for example, the X would be, I don't know, totally disconnected space with infinitely many points. It could be the interval, I mean, closed or open. It could be, open is, this is true for locally compact guys, but okay. X could be the circle, X could be the contour set, and we can compute the semigroup of the continuous function over these spaces. Okay, so it's a really nice tool. And in this case, probably this is uh, something that can be useful at some point. So any element in here will be characterized by a decreasing sequence of open sets. Okay, so it can be written as the supremum of this partial sum. So the indicator map okay. So what it says is that I take indicator map is the map that takes value 1 on certain open sets of X and 0 elsewhere. And I know from the lower semi-continuity of the function that the pre-image of all those guys will be exactly open sets for the Scott topology. So these guys will be open. So the indicator map on some open set is lower semi-continuous function. It's not hard to check. And I just take partial sums of the nth first open sets. And it's not hard to show that these open sets are decreasing. Okay, so this sequence of decreasing open set is really characterizing your map F. And actually, it helps you to characterize also the compact containment relation in this CU semigroup, because we have, so this, for example, can be written as UK. Okay, so a function is compactly contained in another one if any of the UK for F is compactly contained in the UK of J, and we have also that F is compactly contained in the biggest element of this U semigroup. So this means that those open sets will eventually become empty. Okay. Okay. Yeah. So for commutative system algebra, where the topological space is not that big, also the semigroup is really well understood. And probably the point of 3 is to mention what's called one-dimensional non-commutative CW complexes that are being classified by the semigroup. But yeah, probably due to time restriction, I will not enter into those. Okay, let me finish this section of example by stating something that Ramon already told before, is that these hypotheses are really needed, okay? Are really necessary in some sense. So for example, if you look at So the continued function over the two torus, then from one, this thing is a CU semigroup, okay? Because the dimension of X is finite, and this is obviously a semigroup that satisfies any hypothesis you may think of. But this thing will not be the semigroup of the continuous function over this space, okay? Okay, so the way to show this, there are two ways, I guess. One is that to show, so we will see some additional properties in the next course. So this thing is not satisfying a special property coming from concrete semigroups, meaning the semigroup of a sister algebra. And while this guy obviously will satisfy it because it's a concrete semigroup. And also, there have been an explicit computation of this thing, and you can see that there are more compact elements than just constant function here that takes value in a compact element. Okay, I mean, this kind of example we will see what's going on in the second part. Probably it's a good place to stop. Yeah, probably it's a good place to stop. Okay, so take 10-minute break and we resume at 05. Okay, so welcome back to the second part of the session. And so we will continue with some other way to compute or construct or find other CU semigroup in the nature. So we've seen more or less the semigroup of AF algebra, of certain commutative sister algebra, and certain pullback of these two things. And yeah, so I don't have time to enter into this large class of table rank 1 sister algebra that are called one-dimensional non-commutative suitably complexes, but just think of continuous function over the interval, tensor with some finite dimensional sister algebra, so it mixes the two results we've seen, and the morphism here is coming from another finite dimensional sister algebra. So those things are well understood, and we can use this theorem to compute the semigroup of these things. And this class is really large in the stable rank 1 setting, and there is a strong classification result by Roberts, but this is not the main point of this session. But just know that, yeah, this theorem allows to compute the semigroup of a rather large class of sister algebra. Okay, so now see another kind of way to find out CU semigroup is to compute what's called double duals. And while I mention these things, I should also mention a property satisfied by any concrete semigroup, which is called the almost algebraic order. So I mentioned it verbally, but So I recall when I say concrete semigroup, it means that it's a CU of A for some system algebra A, and when I say abstract semigroup, it means that it's just an element, an object in the category CU. Okay, so I briefly stated it earlier, but this is a concrete semigroup, and this is an abstract semigroup, and actually it can be shown that this is not a concrete semigroup. Okay, so not only is not isomorphic to this concrete semigroup, but there are no sister algebra realizing this CU semigroup. And the way to show this is to study some extra properties that are satisfied only by, I mean, not only, but that are satisfied by concrete semigroups. Okay, so why do we get this extra properties or extra axioms? Is because the category CU is way larger than, okay, so probably is way larger than the subcategory of concrete semigroup. Okay, so this comes with a range problem that is actually really hard, I guess. Okay, so those are the concrete one, and those are all the abstract and concrete ones. And in general, I mean, we know that this thing is way smaller than that. And so this range problem, usually one should study property coming from the sister algebra and pass it down to CU of A and probably add it to a definition of a subcategory to try to solve a range problem. So one of them, and it's probably one of probably the first one that has been noticed, is almost algebraic order. So we've seen already that CU of A is not only an algebraic object, it comes with a topology, okay, the Scott topology based on the compact containment relation. So this is really nice because it captures some topology of the sister algebra, but then you lose the fact that the monoid is algebraically ordered, okay? So in general, but almost always, okay, in general. Okay, for example, even in the easiest cases or the most well-behaved cases, such as the Kunsemi group of M to infinity, this will not be algebraically ordered. I recall that the Kunsemi group of M to infinity is this thing, and you can observe that if I take the non-compact version of 1, this is bounded by, I mean, it's smaller than the compact version of 1, but there are no elements that I can add to this non-compact one that will end up being the compact one. Why is that? Is because this subset is absorbing. So any guy that I will add to this will not be compact, but there is no chance to realize this compact one as the sum of this non-compact one with some other elements. And we've seen also, moreover, that for any element that is non-zero, obviously, the non-compact one plus x is okay. So this is greater than the one compact, and actually is non-compact. So this is greater and different. Okay. So even in this nice and kind of elementary case, we don't have algebraic order. But we do get in any concrete Cuntz semigroup, we get something that is close enough to algebraic order, and it's been introduced by Robert, formally, even though some version of it had been discovered earlier, but we start with CU semigroup, and we say that S has almost algebraic order, or sometimes this is called axiom of 5. Okay, to continue the list of other theoretic axioms. So we do have, if we have the following. So if I take any three elements, okay, and I do have that x is bounded by y, and x prime is any cut down of x, then I can find an element such that if I sum this element to the cut down, I will land below y, and if I sum it to x, I will land above above y. Okay, so we cannot hit y exactly, but we can kind of find something that is just below and something that is just above y by summing this element to x prime and x. So it's measured. I mean, that's why it's called almost algebraic order, because it's a weaker form of algebraic order. So there exists an element in S such that okay. So for example, if X is compact, then you actually get this algebraic order. Okay, so because you will get that x plus w is bounded by y, which y is bounded by x plus w, so you get equality. Okay. So if I get that the compact element is bounded by any other element, I can complement these compact elements to hit the greater elements. Okay, so now theorem. So this is primarily due to Rodham and Winter, even though they didn't call this thing almost algebraic order, and this was done in W of A and not CU of A. This was done then, and this was formally written by Robert in this paper. So the semigroup of any star algebra satisfies of algebra. So how does this work? So I start with two elements in T of A that can be realized by positive elements, right? A and B. And I do have this, okay? And now I have to consider any cut down of A and find this W that satisfies this lower and greater bound, okay? Okay, so we've seen this argument a couple times already, done by Francesc and last time in the previous session. Without lots of generality, we can assume that this cut down is actually realized by some cut down of A, like complete cut down of A. Can assume that there is some epsilon such that S prime is actually okay. This cut down of A. I need two epsilon for precision matter. Okay, so now I can use Rodham's lemma, okay, to find partial isometry such that the cut down of A by one epsilon is star V, and VB star belongs to the hereditary subalgebra generated by B. And now we're gonna use heavily functional calculus. So we will consider this function to be the function that takes value 1 and 0, that linearly goes down to 0 at epsilon, and then takes 0 everywhere else. And we will consider, and I mean, it's kind of more an observation that this is 1, that this is orthogonal to this function, okay, the function that gives you these elements. Okay, the orthogonality shows on this diagram. So if you multiply the two, you will get 0 because the support are disjoint. So what does this tell you? It tells you that the functional calculus of this H epsilon, okay, so this is H epsilon, applied to A is orthogonal to the cut down of A by 1 epsilon. And similarly, I apply this orthogonality to VV star. Okay, so I just applied H epsilon and the cut down by 1 epsilon to this positive element, and I also get two orthogonal elements. Okay, and so the functional calculus tells me that this guy is strictly, I mean, yeah, this guy plus this guy are in fact strictly positive in there. Okay, and so we will show that they are consequent to B. So functional calculus tells me that V star. Okay, so for the sake of the proof, probably A is unital, but this will be true in full generality anyway. So now if I just consider not only the positive part of this thing, but actually, okay, the identity minus epsilon plus this h epsilon, I also get a positive function. Okay, this is really trivial to see. And so when I apply this to VV star, it gives me this element, which is a positive element. Okay, so this implies that VV star plus H epsilon VV star is strictly positive in this hereditary subalgebra. So another way to say this is that BV star plus H epsilon plus these positive elements, yeah, is greater than epsilon. And once we know that, we're almost done. Because being strictly positive, then, I mean, this element belongs to the hereditary subalgebra generated by B, so it's going to be Kuntz below B. And upon modifying this a bit, we can get that this is going to be consequent to B. Okay, so more in detail. If I compress this guy by a certain power of B, so namely the square root of B, I get that this compression, okay, so the compression of epsilon times 1 will give me just epsilon times B. And then I compress this H epsilon VV star. Okay. Blah, blah, blah. This is probably now just Kuntz greater than, okay, I mean, yeah. Okay, so I compress by square root of B on the left and the right, and also here. And we know that multiplying by the scalar does not change the Kuntz class. Okay, so this is Kuntz equivalent to B. So, so now let me write this guy to be C. And these belong to hereditary subalgebra generated by B. And this also, okay. So, So we do get this thing, and this thing was already, I mean, B was already super equivalent to this by what I just showed. So they are equivalent to B star plus C. And this is not exactly what we want, right? We want kind of an orthogonality argument. But Francesco already shown that okay, the sum of two elements is Kuntz below their orthogonal sum. Earlier result. Okay, so overall, I found an element C such that the Kuntz class of B is bounded by the sum of A plus C, right? That's what I have. No, not exactly. So this dv star is equivalent to a cut down of A by construction. So we get this first inequality. And I mean, this is what I really get. So VV star is equivalent to a cut down of A, which is equivalent to A. And now I have to show that I want to show that this X prime plus the Kuntz class of C is actually below the Kuntz class of B. But this is this will force down from construction and the orthogonality of this thing.
Instead of B star, then you want B square root of B, B star square root of B. I mean,
yeah, but this will be Kuntz equivalent, right? I mean, where? Here?
Yeah, I mean on the left. So when you say so this happens, the first line should it be like B square root? Why is it equivalent to B star? You know what I mean?
Yeah.
This thing here, yeah. I mean it comes from B square root of B square root of B on both sides. And why does this get over?
I mean, VV star is in AB, right?
That's true, yeah.
So
Maybe it's not a rejection. I mean, it doesn't. I think it doesn't hurt if you still put it.
yeah, okay.
And also downstairs, on the right. That shouldn't change. And then this carries over to the right. But still,
Okay, and then
you still preserve the equivalence from B a half. So B then is equivalent to B a half, B star, B a half plus C. And then you can get, well, here you can get rid of this because you can take the B squares away. Here you go up. Yeah.
if I go up,
Yeah, because B a half, B star, B a half is equivalent to B star.
yeah, okay, yeah, it's true. It's true. Okay, thanks. Yeah. And now to go down, so we have seen that this thing is, I mean, this belongs to hereditary subalgebra generated by B, okay, because this guy is in there, so the put down is in there, and C was also in there, and those two things are orthogonal, okay. Uh, so this tells me that this guy is equivalent to B, and this tells me that this guy, I mean, the direct sum is equivalent to the normal, the just the usual sum. Okay, so overall, I get that uh, dv star minus epsilon plus direct sum with C is equivalent to B. And from construction, this is equivalent to the cut down of A by 2 epsilon. So this translates into the fact that X prime plus C is bounded by class of B, and this translates into the fact that the class of B is smaller than A plus C. Okay. So we get what we want. Okay, I wanted to talk about double duals, but running really out of time there. So probably a quick word on this. So if I take any CU semigroup, there is a way to construct another CU semigroup out of it using kind of lower semi-continuous function from the traces or the functionals, which is a topological space, into the extended positive line, okay? And this becomes a CU semigroup that is called the double dual, okay? So it's been introduced by Roberts in the same paper. So it's a subset of this CU semigroup. I don't want to enter too much in details, but so this thing, we already encountered this, is the space of functionals. So functionals are generalized CU morphisms from S to the extended real line. So generalized means that they preserve everything but the compact containment, okay? And this is compact Hausdorff space for a certain topology, which is called the interval topology. Okay, so you have to approach an element by a net such that the lim-inf and the lim-sup actually hit the element you want. I mean, this is technical details, so Okay, and the theorem is the following: is that okay, this subset I don't really precise what it is, but okay, never mind. So SR is a CU semigroup, and actually we will see in the next session some bit about tensor product, and you can show that this thing is always isomorphic to this tensor product. Okay, and if S satisfies O5, this is the theorem of the paper, then so does the double dual. Okay, and the last category of conservative I wanted to present is conservative group of a really important class of C-star algebra, which is the simple stable, stably finite C-star algebra. So we've mentioned the Elliott classification program, and those are the C-star algebra of the Elliott, more or less. I mean, okay. So recall that the Elliott invariant that classifies more or less this C-star algebras. I mean, you have to add other assumptions, but okay. So this Elliott invariant is case theory and traces, right? And recall also that for stably finite C-star algebra, we have that the K0 group is in disguise the compact containment of the conservative group. Okay, so it's not really surprising that the conservative group is recovering more or less K0 and the traces via this generalized CU morphism. And so the theorem goes as follows. So this has been shown by Brown, Pereira, and Gomes in 08. And there has been some other reformulation using functional instead of traces by Elliott, Robert, and Santiago in 11, and is converted by represent. So for this class of C-star algebra, simple, let's stable, stably finite algebra, we have the following dichotomy. So either A is purely infinite, and in this case, the concerning group is collapsing, so it doesn't see much information. We just have 2 points, a 0 and an infinite. And yeah, you guess what happens there. Or, okay, probably should erase this. A is stably finite. And in this case, we have a really nice description of the concerning group. Also, I mean, there, but it's kind of useless. CU of A is gonna be divided in 2 parts. So we have the compact elements. So it's given by equivalence class of projections. So those guys are compact. And the non-compact guys will be given by the double dual. Okay. Okay, so I wrote it differently. So. And we have to take out the zero element because it's already in there. Okay. So how does the order and the sum are defined? So obviously on each subset it's defined. I mean, it's as natural sum and order structure. But whenever I sum a compact with a non-compact, then the same will happen as the toy case of the semigroup of UHF algebra. Okay. So the double dual will absorb compact elements. So we have the Cuntz class of a projection with some lower semi-continuous function from the cone of functionality to the extended real line. So those elements are really function from this topological space into R plus. Okay, so I will write them by letter F, G, and so on. So this is really the function that evaluate any functional on the Cuntz class of P. And I do the sum in this subset, in this submonoid. Okay, and probably it's also going to be non-zero. So recall that P hat is a map from this topological space into there, and to a functional, I just evaluate the functional at this compact element. And the order goes as follows. So it's kind of the same thing that a non-compact element is bounded by a compact element if, when I look at the non-compact version of this guy, it's still bounding F. And a compact element is bounded by non-compact elements if this function is algebraically bounded by F, meaning that I can find some G in the double dual, which is not zero, such that the evaluation at the compact elements plus G is hitting F. Okay. So this is an abstract generalization of the mixed sum and order that happens in the semigroup of UHF algebra, for example. And okay, so remark, observe that in the stably finite case, we have that K0 is given, I mean, the information is really the information of the Murray-Neumann semigroup, which is really the compact element of the full semigroup. Okay, and traces is nothing more than functionals. Okay, so in this case, probably units Z stable and simple.
Okay, or exactly.
But it shows it's stable and simple.
Well, if we get quasi-braces on, so.
Yeah.
This is a blue.
Um, so the point of this remark is that the Kuhn semigroup in this case captures everything about the Elliott invariant except for K1. So it can be shown that the pair CU K1 in this stably finite, that's stable, simple. This gives you the Elliott invariant information. Okay. But we can actually do better in this case. Okay. We can actually incorporate K1 into some refined or augmented version of Kuhn semigroup to actually recover, to get an equivalence with the Elliott functor. Okay, so this is going to be the last part. And I wanted to do the proof, but I don't think I will have time. So in what follows, A is simple, Z stable, stably finite star algebra. And so how can one get K1 from a certain kind of Kuhn semigroup? So the way to do so is by observing that we have this Kuhn formula. The K1 is actually inside the K0 group of a tensor with continuous function over the circle. Okay, this is not true in full generality, but whenever we have those hypotheses, then this becomes true. And this group of projection is giving you the group of projection of A and the group of unitaries of A. Okay, so we have a way to recover in this special setting to recover K1 from some positive elements, okay, or projection in that case. And based on this, the equations, A showed that, it's kind of a reformulation of the above, that the Murray-Vandermeer semigroup of this sister algebra is a zero element union V of A without the zero Cartesian product with K1 of A. Okay. So what's important to notice is that projection in this there are way more than just projection in A, okay? And you will get, so that's why in this no K1 obstruction, we get this nice description of this Kuhn semigroup in terms of lower semi-continuous function into CU of A. But whenever you have K1 obstruction, then the Kuhn semigroup that you consider is not big enough, okay? There are more compact elements. And this is what just following theorem will show. So the question is, the third question is, does the concentric group of this star algebra contains the Elliott invariant? And the answer is yes. So I recall we are in this special setting, simple as stable semi-finite. So the answer is yes by the following theorem. So this is built up on the work of Thickwisses, and the main theorem has been proved by Joachim Cuntz, Pereira, and Santiago. 14. Let A be at 4, and the concentric group of this system algebra, so tensored with the circle algebra, will give you something really nice. So on one hand, we have this non-compact guy of the lower semi-continuous function over the circle into CU of A, and the compact element will be this thing down there. Okay. And you can show that those things are related to the double dual and so on. Yeah, I should probably mention the sum and order. I mean, yeah. So in here, we say that a pair here is bounded by another one if the following happen. So either they are equal component-wise, or the compact element there is strictly smaller than the compact element here. Okay. Then the sum is component-wise also. Then an element in here, sum by an element in there, will give you also an element in here. So this is F plus the map that evaluates that takes value, constant value x. Okay, so this is a lower semi-continuous function from the circle into CU of A. And the sum of the two will not be compact. So I have a proof for this, but I guess I will not have time. And an element in here compares with a non-compact element there. Well, we do the same thing. We compare everything in there. So if the map, constant map that sends e to x compares with f in the double dual, I mean, yeah, not the double dual, but in this concentric group. Okay. Probably probably out of time. No, I still have a few minutes. So a brief sketch of the proof. The hard thing is that in general, we don't have this local to global behavior of the Kuntz superequivalence relation, okay? And so the first step is to describe the Kuntz superequivalence in this algebra, okay? And there we have K1 obstructions, so the previous result will not apply. And for example, you can show that projection P uh, I mean, for a projection P in here, there exists a projection in A, such that point-wise, this projection is equivalent to this projection, okay? Such that P of T is equivalent to QP for T for the circle, okay? So this tells me something that is really nice is that in particular, the compact element of this CU semigroup is B of A, okay? Because any compact guy will be a constant value function with value in B of A from this result. So here we see that this CU semigroup will not be enough to describe this concrete semigroup because from Tiquis's results, the classes of projection of this thing is not only VOA, it's VOA, and you have this K1 group that produce a lot more compact elements. Okay, so this is more or less the intuition behind this. And so this is for projection and for a positive element F, and we have to take it not equivalent to a projection, then the local pass to the global. Okay. So this hypothesis is important because you could have some global things that are locally equivalent to a projection at each point, but globally is not equivalent to a projection. Okay, so this is the idea behind the description of this thing. And then, okay, one more minute. This is step one, and step two is that from the preserved result, we know we have a natural map. I mean, homomorphism actually. Beta. So any Kuntz class of this guy will produce a lower semi-continuous function over the circle with value in C U of A. So to F, I just assign the bondwise map. Okay. So I have a function from the circle into A, and its Kuntz class will produce an element in there, sending to any point of the circle the Kuntz class of the function evaluated at this point. Okay. And so whenever we had no K1 obstruction, this was an isomorphism. And from the argument that I stated earlier, the compact element in there will be just B of A. But the compact element in there, we've seen that there is more than B of A. So the intuition behind is that this is too large to be isomorphic to this. But you can show that we actually get a surjection, and now if I call Okay. If I call this guy T, I also have a map from here. Okay, so we have there the beta, which is surjective. We also have a map alpha from T. And the surjection of beta tells you that any non-compact guy here will be hit by some guy in there, okay? And obviously, by T-quizz's results, this will be hit by some projection in there, okay? Because this is, okay, by T-quizzes, we know that this is the Murray-Vanderman semigroup of the algebra. So any guy in there is realized by a projection in there. And from the subjectivity of beta, we know that any guy in here is realized by some positive elements in there. This is more or less the idea. So we get the subjectivity here, and we want to show the order embedding parts. And this is based on 1 and 2, okay? So order embedding, embeddedness of alpha uses 1 and 2, and I don't have time to actually show this to you, but it's not so hard, okay? So yeah, probably should stop here. Sorry for overtime.